Thank you, madam, for such kind words for me. And I would like to thank Professor Panigrahi sir for giving me this opportunity to present my work. And is the screen visible, sir? Hello, madam. Am I audible and the screen is
You are
shared?
audible and your screen is visible. Yes.
Okay, thank you. So I will be talking about digital quantum computation of atomic systems on NISQ devices. So as the title suggests, it's a digital quantum computation, means the computation that we have performed are with using quantum gate and circuits. And we are using them for studying properties of atomic system, and it can be extended to molecular system as well. And the devices that we are using are the NISQ devices, or the quantum computers that are available for us now in the NISQ regime. So these are my outlines. I will start with the basic introduction of how we are approaching towards the problem of atomic and molecular physics using an algorithm called variational quantum eigensolver, and how we are preparing the Hamiltonian as well as these answers. And recently we have also used quantum information ideas to construct the circuit, and that also I would like to present. And also about the current hardware scenario, how one can run their jobs on quantum hardware, and how difficult or easy, or what are the things that one have to keep in mind while constructing the quantum circuit and the other things. So my talk would be focused on my two of this work, and these two works are based on the VQE algorithm. And one is for the hydride ion calculation, where we did the ground state energy calculation, and the second one is that where we proposed new answers from our side. So quantum many-body system is one of the very key application of quantum computers, and in principle, large-scale fault-tolerant quantum computers have this potential to solve this electronic structure problem very efficiently. But but these devices are expected to be in many years away from now. So at present, what the devices we have are the noisy intermediate scale quantum devices, or the NISQ devices, which have limited circuit depth, limited qubit connectivity, and there are some errors in every operation. Every single qubit to qubit gate operation comes with error. And because of this constraint, fault tolerant algorithms are nowadays difficult to run on the current hardwares. But there are some algorithms such as VQE has been emerged, and recently another algorithm called SQD, or sampling-based quantum diagonalization. These are being highly used to run on the NISQ devices. So what it does is takes a quantum circuit, it executes on a quantum computer, take the basic states or the bit string, whatever you call, and then optimize it in a classical optimizer, and then feed it again. So VQE has been, in many years from now, it has been used many times by multiple researchers for the ground state calculation, properties calculation, PDM calculation, other kind of things. But in the relativistic regime, it has been lessly explored. So in our group at TCG-CREST, we have studied PDM, hyperfine structure, and other kind of works also using the VQE. And these two papers you can refer to see how different properties of atom in a relativistic regime can be solved. So as the name suggests, variational quantum eigensolver, it is based on the variational principle. And the variational principle we have all studied in the quantum mechanics, where we know the Hamiltonian of a system. Let us take any Hamiltonian. We know the Hamiltonian, but we don't know the wave function exactly. So we start with a trial wave function psi, which has some parameter theta. And then we calculate the expectation value, and it should be greater than or equal to the true ground state energy. So to approach that, we change the parameters slightly, theta1 plus delta theta1 sum, and then minimize it. And we do this again and again, up to which we found the minimum energy, or which is we are calling as ground state energy. So this principle has been used for the VQE algorithm exactly. For example, this psi theta, h, and theta. How did they look in terms of quantum circuit? So as we are talking about atomic system or molecular system, let us take helium. We know it has two electrons, one s, and if in terms of we talk about spin orbitals, we know 1s2, 2s2, 2p6, and these are the spin orbitals that can be present. So as there are only two electrons, and electrons have spin up or spin down. So this arrow up is plus half, arrow down is minus half, and so on. For example, let's construct 1s2 orbital. How it will look like? It has two two spin orbitals, one is up and one is down. In helium, two electrons are present, so they can very comfortably go and sit there. So two ones could be present there. So wherever the electrons are present, we will denote it with 1. And where the electrons are not present, we will call them as 0. So in this way, we prepare the qubit, two-level system, 1 and 0. So 1, 1, 0, 0 is a configuration we can tell for helium. So this way we prepare qubits. Now talk about Hamiltonian. So the Hamiltonian generally in atomic and molecular systems are in a second quantized formalism or in a very complex way. But for the easiness of our today's discussion, let's consider in terms of polymatrices. The Hamiltonian that we have are in terms of the polymatrices, which are the X, Y, Z, and I, combinations of polymatrices. And the wave function, we know the qubit, we know how to, we have the Hamiltonian, we construct the wave function, psi theta. So psi theta is nothing but the quantum circuit that we are using. And here the theta is the rotation angle that are present on the 1 qubit gates or the 2 qubit gates as well. Some 2 qubit gates that we can create, not the CX1. Okay, so the psi theta is our quantum circuit that can be prepared. Let us suppose we start from an initial state phi naught. We will act an unitary onto it, and this unitary is the quantum circuit, which can look like this combination of different unitaries. And inside the unitary, these quantum circuits are present. And the quantum circuits are made up of single qubit gate, 2 qubit gate, measurement, and the input state that we're preparing and so on. So the VQE algorithm, as we discussed, is based on the variational principle. We prepare the quantum circuit, and then we minimize it through the Rayleigh's variational principle. We start from the initial Hartree-Fock state, apply the unitary U theta, and then measure it. Then calculate the ground state energy E theta, and pass it through a classical optimizer. If it is not converged, then we update the parameter theta, and then redo this whole operation again and again. But this kind of algorithms comes with a challenge also, hardware noise. If you have prepared a deep quantum circuit, that can be also a big issue because each operation comes with a noise. So these are some limitations of VQA also, that if we have a very long or deep quantum circuit, or it's have a lot of 1 and 2 qubit operation, it may yield wrong eigen energies because of the noise. We start, these are the operations that are handled with the classical and quantum computer. It's a hybrid algorithm. We start for the second quantized Hamiltonian. For now, whatever Hamiltonian we have, we encode in terms of the polymatrices. So let's start from this one. The Hamiltonian that we have are in terms of the polymatrices. Then we generate the answers, do the measurement. These optimizers are the softwares which change the parameters. Taking a simple example, we have two terms, Ix, three terms, Ix, Iz, Xy. So these are the Hamiltonian terms which are in terms of polymatrices. And once you measure it, the circuit psi, at the end, what we are doing is calculating the ground state energy of each of the term. Psi, H psi, it means expectation value of Ix, Iz, and Xy. And then we are adding up. And the qubit Hamiltonian construction means any second quantized Hamiltonian which are present in the creation and annihilation form that can be transformed using a method called Jordan-Wiener transformation, where each creation operator A dagger has this form in the polymatrices, and annihilation A has this form. Now comes to the answers, because it has a lot of different type of answers one can construct, and in community a lot of different ways are there through which you can prepare the answers. And the VQ algorithm is much more dependent on the answers also, because if our trial wave function is highly accurate, so we are guaranteed that we are going to get the correct ground state energies. So one such answers is unitary couple cluster answers, or it is basically called as UCC answers, and it is based on the classical formalism called coupled cluster theory, where we take excitations from the Hartree-Fock state and so on. For example, let us take phi naught or the initial state. So the initial state in our case is the Hartree-Fock state, or the state from where we are starting, and then this exponential ET is the operator which is acting on the initial state. And this T can be T1 plus T2 and so on, where T1 is a single excitation cluster operator, double excitation, triple excitations, and so on. So the unitary form psi UCCHT is written as this. So there are several combinations also you can prepare. This is the UCCSD answers. You can take single excitation, double excitation, and so on. If you want to modify it, you can take only pairwise excitation, or you can take singlet excitation, where in each excitation they have different spins. So it is up to us that which kind of answers we want to prepare. But at the end, we also have to keep in mind that we want to land it in a minimum ground state. Another one. So one of the drawback of this kind of answers is they're highly accurate, but for the current devices, it requires a lot of quantum gates and quantum operation. So for the current devices, it becomes very heavy, and the energies we may not find very accurately in the hardware. But in a simulation or other kind of property, they are highly accurate. Another one is the hardware efficient answers, and these are not physics inspired. They doesn't have the information about the problem that we are solving, and then these are just prepared with the single qubit gates and two qubit gates and some architecture. And these kind of blocks are repeated many times. So the advantage is that we have less number of one and two qubit gate. But as we don't have the information about the system that we are solving, then it is dependent on the problem that whether we are getting the correct ground state energy or not. So it is not reliable at all. But if one can modify the hardware efficient answer such that it can keep the depth low, but also know the physics behind the problem that we are solving, then it might help us. So we initially we have tried to solve about the hydrogen H minus ion. So it has two electrons, and it's a very highly unstable ion, and it has a lot of applications. So for that studying, we have used different kind of physics inspired answers such as the UCCSD, pairwise Q UCCSD, and so on. So in all the cases, we can see that the UCCSD answers, which understood the physics behind the problem, is always giving the correct or the reference energy that we need. But at the end, if you use the hardware efficiency kind of answers, if you may zoom into this, we will find that the values are not that much accurate. So it depends on which kind of hardware efficient answers or physics inspired answers that we are using. So in correct physics, the unitary coupled cluster answers is the answers one can use. And again, another problem that we face while executing on quantum hardware is the errors. For example, if you run the Bell state, for example, we are expected to get these states which have the same probability 0, 0 plus 1, 1 by root 2. But on hardware, we can see it have different, means other states are also been appearing. These are happening because in the noisy devices, each operation that we are doing, and there are multiple noise present. There are coherent noise, incoherent noise, measurement errors, and other kind of things. One have to also deal with these things. For example, if you want to measure the expectation value of Z matrix, I'm sorry for the diagram that I have prepared by hand, but if we take Z matrix and try to find the expectation value, it should land -1 or 1. But we can see if we increase the circuit depth, one can see that the values, it should be at 1 or -1, but again, it has been dropped to this scale. So this is happening because of the different kind of span noise, incoherent noise, projection noise, and other kind of things. And this is a very good reference by Zlatominev, which have explained all these kind of noise that are present on the quantum device. And I will encourage others to also go through the reference. So in our case, we use the Z and E, or the zero noise extrapolation. So there are several ways one can do the error mitigation. So error mitigation and error suppression, they are two different things. Error mitigation we can do by zero noise extrapolation or read out error extinction and so on. So these are done by using the quantum circuits. But error suppression, they are work in the pulse level, because whatever the operation that we are doing in the superconducting devices, they are working in terms of pulse. So dynamical decoupling, polytwirling, and these kind of methods are for the error suppression. But again, we come into the same picture that if UCCSD is highly accurate, but it yields higher 2 qubit gate count, circuit depth count, 1 qubit gate count, and so on. So is there any way we can tell the system or any hardware efficient answers that we are solving this problem, but we have to keep the circuit depth also very low, because growing circuit depth causes two issues. One is the hardware noise that we talked, and also the trainability of answers parameters. We can see that in hardware efficient answers, a lot of parameters are there. So if you have a lot of parameters, then they become very difficult to optimize also. And the devices that we have nowadays for the IBM hardware, they are not all to all connected. Unlike, so in that case, if the two qubits are separated by a long distance, then there will be swap operation between them, and the circuit depth can then again explode. So we have to keep in mind that also. So in our work, we prepared hardware efficient answers, which have a shallow depth, low gate count, and it also respect the physics behind it and solve the problem very accurately. And we have named that as quantum information inspired answers. And for that, we have used two quantities. One is the von Neumann entropy, and another is the mutual information. And in the previous talk, Professor Mukherjee also explained about Shannon entropy. It is the similar one for the qubits, which is the von Neumann entropy. We start from a wave function psi. Let us take a system A and B, and then we calculate the density matrix, the diffuse density matrix, and this is the formula for the von Neumann entropy. So this explains us how each qubit is entangled with the rest of the system. So von Neumann entropy is a measure of entanglement, how much entanglement is present in the system. Another one is the mutual information. If we have two subsystems A and B, how much quantum correlation they are sharing, that can be calculated using the mutual information. For that, you need the von Neumann entropy of this system, SA, SB, and this SAB. And then this is the formula for the mutual information. So how one can use this for the atomic and molecular physics? Let's again come back to the spin orbital formalism. So qubit 0, qubit 1, qubit 2, qubit 3, and so on. These are present. So we can measure von Neumann entropy of each qubit. For example, qubit 0, we make a bipartition of qubit 0 versus rest. And then we can find out how much qubit 0 is entangled with the rest of the system. Similarly, qubit 1 is entangled with the rest of the system, and so on. So we prioritize that qubit which have highest von Neumann entropy, and the entangler positions are being determined using the mutual information. Whichever two qubits has higher mutual information, we give them first position in the circuits. Let's see in terms of circuit. It is the initial state, Dirac-Fock state or Hartree-Fock state, whatever it say. It starts with the rotation angle, and these are the two qubit gates. So you can see here I have written CT and TC. It means control target. Let us say that qubit 0 has the highest von Neumann entropy. So qubit 0 will have always the control in the first position. And in the second one, the second bipartition, we will tell TC. It means the qubit 0 will have the target, and all the other qubits will have the control. So this is the block for 1. This is block 1 for qubit 0. Similarly, different blocks can be constructed. And these two qubit gates that we have used, are compromised, means composed of these kind of gates. So what we solve here, in hardware efficient answer, they can be linear, fully entangled, circular entanglement, and so on. But we can calculate, by avoiding this, we can calculate mutual information and von Neumann entropy to figure out which are the important qubits and see how much quantum correlation they are sharing, and then construct the quantum circuit in that way. So this helps us, for example, the hello.
Yes.
Is there any noise? Okay. So we can see the number of 1 qubit gate, 2 qubit gate, and circuit depth in all the cases of QIIA, or the quantum information inspired answers that we've constructed, are very low. And still they achieve chemical accuracy, and all are in a very good agreement with the UCCST answers, or with the classical reference energy, which is the CASE, complete active space configuration interaction energy. And we have tested these for many atomic systems, for example, boron plus, carbon 2 plus, and so on, up to 12 qubits. But to test on, okay, and another one, this one is telling that if we use the mutual information ordering, we can see we are all, this bluish region is for the correlation energy. We are almost getting all the correlation energy, but uh, the ordering that we have used for the mutual information is yielding always the minimum difference in energy. And for the hardware run, so for the hardware run, if the circuit depth is very high and also the Hamiltonian terms are very large, then we have to do the resource reduction. So for that, we have followed two ways of resource reduction. One is we have reduced the number of Hamiltonian terms, and in other part, we have also reduced the circuit size. So for the circuit optimization, we have removed small rotation angle. We know that in each 1 qubit gate operation, the angles that we have, if the angle is very low, we remove them because they will not affect that much in the calculation. So at the order of 10 to the power minus 3 or 10 to the minus 4. And then we perform Qiskit level 3 optimization, pi ticket optimization, and so on. And then we convert it into the hardware gate set, whatever hardware that we want to execute. And to deal with the number of Hamiltonian, so again, I want to tell that poly number of terms in the Hamiltonian for any atomic and molecular system grows as n to the power 4. For example, for a 10 qubit system, it can be 500, 100, but if we have larger qubits and larger number of electrons are present, they can grow very, very rapidly. So we have to minimize that also. So for that, we have used the term called cliques. So we have composed each of the polyhamiltonians, which are qubit-wise commuting to one another as cliques. So now, instead of measuring all the single Hamiltonians at a time, means each time you can measure one terms from each clique, and other cliques can be measured similarly. For example, let me maybe by an example I can explain. Yes. For example, I'll start with the circuit optimization part. We can see the abstract circuit, the circuit that we have prepared. It has CX gate count of 72, depth of 182. So we remove the small rotation angles. So now the CX gate count has been dropped 50. Depth has also been reduced. Then we again do Qiskit level 3 and pi ticket kind of optimization, where the CX gate count remains 50, but the depth has been reduced. So now we have a smaller circuit in comparison of the initial circuit that we had. And then when we send it to a IBM quantum hardware, we have to convert it into its native gate set. Means each quantum hardware has its own native gate set, and the IBM cellbook that we have used here, it have a native gate set of RZ, SX, ECR, and X. So we have to convert whole quantum circuit to this basis gate set. And as the qubits are not connected to one another, means all to all connected, the depth can increase again. So we have to really work hard on optimizing this part, because if your abstract circuit has itself large CX gate count or depth, then while transpiling into the quantum hardware, it can explode. So one have to also focus on the circuit optimization part. And regarding the cliques, for example, the original Hamiltonian we had has 464 polyterms, but when we group them in terms of the mutually commuting polyterms, the number of cliques form as 209. And then if two cliques are giving same amount of energy, then we are calling them as super cliques. So there are 18 super cliques that we found. So instead of measuring 464 polyterms for each polyterm, we have to measure the quantum circuit. We only measured 18 super cliques. And for the results that I have shown here, we have only measured here 2 super cliques, where 3 cliques have been there. And you can see that there are 3 results we have. One is the state vector result, which has no noise, nothing. And this QASM or the quantum simulation has also no noise, but it works in the terms of sorts, similarly as the quantum hardware works. And we can see their same amount of energies. But as the hardware has some errors or some noise are present, we are not able to get to the true ground state energies. But in the simulations, we are able to get energies very accurately. So these are the things that I wanted to discuss, that how can you prepare a quantum circuit for solving atomic and molecular physics. How to optimize them, because the qubits and the current hardware intelligence support all-to-all connectivity. How to reduce the number of Hamiltonians, and yes, how to use quantum information ideas so that you can compact the circuit. And I would like to thank my collaborators uh, for helping me in many discussions and everything. And I would also like to thank Professor Panibhai again to inviting me to present my work. And these are the very important references for VQE if one is interested to look how VQE works and so on. So these are very important review articles which shares a lot of information about how VQE and variational quantum algorithms works. And these are some additional references. Thank you. So I can take questions now if you have any.
Okay, so any questions?
I have one question. So,
Yes.
thank you for a very interesting and informative talk. I think it was question is related with Hamiltonian with label T2. This was before HEA slide.
Yes.
So,
Hmm.
yes, T2, yeah. So here you are using fourth order. I mean, if you consider annihilation and creation operators,
Yes.
so total degree is 4.
Yes.
And this is a 4-way mixing process, as sometimes people call. My question is, why you are using fourth order? Why not sixth? Why not eighth, and so on?
No, they can be used, but there is some principle. There is a theorem called BCH expansion and other kind of expansion. There are theorems in atomic and many-body theory, which tells if we have an initial state of Hartree-Fock, so they automatically truncate at the second level in the T2 kind of things. But in principle, you can go, yes, in principle, you can go to the other excitations also. But it is seen that if you use up to second means double excitation, it is called the double excitation. For example, if you have a Hartree-Fock state phi naught, what you are doing is that you are taking excitations from the Hartree-Fock. For example, it is 11100. You're taking excitations here. You can see one that were present in the third position has been jumped to the fourth position. We're calling them as single excitation. Similarly, if two jumps, it is called the double excitation. And that you are telling that why are you not taking sixth order excitation, seventh order excitation? It means at a time you are exciting 6 electron from one orbital set to another one. So in principle, double excitation and single excitation combination, and up to the third excitation also, which is called the CQST-T, usually gets the correct ground state energy, and it is considered as the gold standard. So, and also while focusing on the current hardware scenario, we are also restricting up to the second excitations. But in principle, yes.
Could you name the, I think, theorem which you mentioned?
BCH, Baker-Campbell-Hausdorff expansion.
Sorry, could you repeat once more?
Baker, BS, yes. Baker-Campbell, CAMPBEL.
Yeah. So this is disintegration. Okay. So you're using
Hausdorff,
that one to.
is it?
Yeah, Baker-Hausdorff. I think the theorem.
BCH.
BCH. Yeah. Baker-Campbell-Hausdorff. Yeah. Okay, thank you. You are just using two terms of your expansion and then canceling remaining terms.
Yes.
By using that. Okay, thank you.
Yes.
Okay, any more questions?
Abdul, nice talk.
Yes.
How, just for the sake of confirmation, how does this thing compare now with your very good DFT simulations?
DFT simulations, I have not done, sir. Means.
I mean, for example, literature, typically literature.
Literature, yes. So we generally compare with respect to the complete active space configuration interaction. So we are starting from a mean field theory, Hartree-Fock theory, and then we are solving the configuration interaction problem. So whatever energies that we have done and so on, we are comparing with respect to the configuration interaction. So
Okay.
configuration interaction and the couple cluster energies, we have not compared with the DFT. So
Acha, okay.
maybe I
Got it.
can't answer this one.
Got it. Nice. Yeah.